We went to the moon in 3 days with 1960s technology. So why in 2026 is Mars still completely out of reach? In this video, we're going to break down, step by step, why Mars is on a totally different difficulty setting and what absolutely has to change before anyone can seriously risk the first crewed flight. Start with distance, but in real numbers, not just far. The average distance to the moon is about 384,400 kilometers, around 239,000 miles. That's big, but it is still local space. It is Earth's backyard. In the Apollo era, you could cross that gap in roughly 3 days, and your target, the moon, stayed locked in a simple orbit around Earth, always close in both distance and timing. Now compare that to Mars. At its closest approach, Mars is about 56 million kilometers away, around 35 million miles. At its farthest, it is more than 400 million kilometers, about 250 million miles. So you are not multiplying your distance by 2 or 3, you are multiplying it by hundreds. That alone changes how much fuel you need, how long you travel, and how long your crew is exposed to every danger space has. The other problem is not just how far Mars is, but how it moves. The moon orbits Earth in a tight, neat loop roughly every 27 days. From a mission planning point of view, it behaves like a nearby, predictable target. Mars does not orbit Earth, it orbits the Sun on a path that is slightly tilted and slightly stretched. Earth also orbits the Sun at a different speed and a different distance. So when you aim for Mars, you are not shooting at a fixed point in front of you, you are aiming at where Mars will be months in the future, while both planets keep moving around the Sun at tens of kilometers per second. A small error in timing or direction does not mean you land a bit off. It can mean you miss the planet entirely and waste the entire mission. So distance and motion are already hostile, but that raises the next question, the one that really turns Mars from a trip into an ordeal. How long are you actually stuck out there? For the moon, the timeline is short and tight. Apollo missions took about 3 days to get from Earth to lunar orbit, then a few days on or around the surface, then a trip back of a few days. Total mission length, roughly 8 to 12 days, about a week and a half. Long, risky and intense, but short enough that you can design systems to last that long, with reasonable confidence, and you know your crew will not be stuck away from Earth for very long. For Mars, the standard fuel-efficient path, called a transfer orbit, takes around 6 to 9 months one way. During that time, your spacecraft is travelling around the Sun at speeds of tens of kilometers per second, roughly 24 kilometers per second, about 54,000 miles per hour, but the scale of the orbit is so arduous that it still takes most of a year to close the distance. For a crew, that's not just a long trip. It is hundreds of days of continuous exposure to vacuum, microgravity, and radiation. Every day their bones lose density, their muscles weaken, and then their bodies absorb high-energy particles they would never see on Earth's surface. Now you might say, fine, the trip is long, but why not just leave whenever we are ready and travel when we want? Why does timing make Mars so much harsher than the moon? This is where orbital mechanics adds a new layer of difficulty. You can go to the moon almost any time as long as your rocket is ready, and your trajectory accounts for where the moon will be in a few days. The exact launch day is flexible. With Mars, you do not have that freedom. The orbits of Earth and Mars line up in an efficient way only about every 26 months, a bit more than 2 years. During those launch windows, the geometry is right so that if you leave Earth with a reasonable amount of fuel, you can intercept Mars after those 6 to 9 months. Outside those windows, you can still, in theory, go, but you would need far more energy or accept even longer travel times, which quickly becomes unrealistic for human missions. So if your rocket or your life support are delayed, and you miss that launch window by a few months, you do not reschedule for next week. You wait for the next window, more than 2 years later. That means planning a Mars mission is like planning something that can only happen in rare, sharply defined time slots, and if anything slips, the entire schedule can jump by years. The moon does not punish you like that, Mars does. That leads directly to the next uncomfortable question. If the journey is that long and the launch windows are that rare, what does that do to your overall risk? Because every extra day in space is not neutral, it multiplies the chances that something will go wrong. On a lunar mission, the whole timeline from launch to landing back on Earth is on the order of 10 days. Systems have to work, but they only have to work for a short period. If a piece of hardware has some small chance of failing per day, the total probability of failure over 10 days is still manageable. For Mars, a realistic mission profile looks like this: 6 to 9 months to go there, potentially around 500 days on or near the Martian surface or in orbit, waiting for the next favourable alignment for the return trip, and then another 6 to 9 months to get home. The total is around 900 days, about 2.5 years. Over that time span, every risk grows. More time for a seal to develop a leak, for a computer to glitch, for a pump to wear down, for small cracks to grow under thermal stress. More time for micrometeoroids, tiny pieces of rock or metal flying through space to hit your ship. More time for solar flares and irradiation storms to happen. The statistical chance that everything stays perfectly within limits across all systems for the entire mission drops, even if each individual component is well engineered. So then the next logical question is, if something really serious does break halfway, do you have a realistic way to abort, or are you effectively trapped on your path? This is where the difference between the Moon and Mars becomes brutally clear. On the way to the Moon, Apollo used trajectories that could act as a kind of safety net. In the Apollo 13 accident, after the oxygen tank explosion, the crew used a free return path. That means their trajectory around the Moon naturally curved them back toward Earth, even without large extra burns. The time to return was still just a few days. They were in serious danger, but they were not months away from home. On the way to Mars, that kind of quick return is not available. By the time you're halfway to Mars on a typical transfer orbit, you are still many tens of millions of kilometers from Earth, and you are moving on a path defined by the big burn you did leaving Earth orbit. To turn around and come back faster, you would need to fire your engines for a very long time in the opposite direction, burning an enormous amount of fuel that you did not and cannot carry, because that extra fuel would have made your rocket far too heavy to launch in the first place. Your course is locked in by conservation of energy and momentum. In practice, an abort on a Mars mission might mean skipping the landing, staying in orbit, and using Mars's gravity and a carefully planned burn to swing back toward Earth when the alignment allows it. But that still means being away from Earth for many months. There is no option where a major failure happens today, and you are safely back on Earth a few days later. Once you commit to a Mars transfer, you accept that you will be far from home with no fast rescue for years. So just in this first layer, distance, motion, travel time, narrow launch windows, multiplied risks, and no quick aborts, you can see why Mars is not just the Moon, but further away. And the tough part is, this is only the beginning. Because after the universe hits you with time and distance, it hits you with something even more unforgiving. The cold exponential math of how much energy and fuel you actually need to make that trip at all. You got a rocket off the pad, you reached orbit, so why isn't it just add a bit more speed and go anywhere in the solar system? The harsh answer is that spaceflight is ruled by something called delta V, total change in velocity, and the way fuel scales with delta V is not friendly. It's brutal. To get from Earth's surface into low Earth orbit, you already need roughly 9.4 to 9.7 kilometers per second of delta full. That's about 21,000 to 22,000 miles per hour of speed change stacked up through different engine burns. That's just to reach orbit, just to be in that 400-kilometer high loop around Earth. From orbit to the Moon and back, you add a few more kilometers per second. Apollo needed a big push from low Earth orbit onto a path that would intercept the Moon, then some more for braking into lunar orbit, landing, taking off again, and coming home. It was extra, but still within a manageable margin on top of that initial 9.7 kilometers per second. For Mars, the bill jumps. From low Earth orbit, you need around 3.6 kilometers per second just to escape Earth properly and get onto a good transfer path to Mars. then you need about 1 to 2 kilometers per second more to slow down into Mars orbit. After that, you still have to land, which takes additional delta V, and later, if you want the crew to come home, you need more delta V to launch back off Mars, get into orbit, and head back toward Earth. Here is where the Tsiolkovsky rocket equation comes in. You do not need the formula, but you need to understand the shape of it. Every extra kilometer per second of delta V does not cost you a little more fuel, it costs you exponentially more fuel. You want one more small chunk of speed, the required propellant mass multiplies. You push the delta V higher and higher, and the rocket turns into a giant stack of fuel with a tiny useful payload on top. So the question becomes, if this equation is punishing you for every extra kilometer per second, how did Apollo still manage a full round trip to the moon with a single launch? And why can't we just do the same thing to Mars? Apollo pulled this off because the mission profile stayed tight, short, and focused. The Saturn V, the giant rocket of that era, could put about 140 metric tons into low Earth orbit, roughly 310,000 pounds. That mass included the third stage, the lunar module, the command and service module, and the fuel needed for the next big burn. From that parking orbit, the Saturn V's upper stage performed a translunar injection burn, adding around 3.2 kilometers per second of delta V. That was enough to send the spacecraft stack on a direct path to the moon. The rest of the mission used smaller stages and precise maneuvers, but the key point is this: the stack was designed for a short, sharp campaign. Apollo did not need to carry years of food, water, and spare parts. It did not need thick, heavy radiation shielding for a multi-year voyage. It did not have to include a massive habitat designed to keep people alive for 900 days. The life support load was on the order of days, not years. That kept the total mass low enough that a single Saturn V could handle the whole thing in one go. So here's the uncomfortable follow-up. What happens when you try to scale that same one big rocket, one clean mission idea up to Mars without changing the rules? If you try to run a Mars mission with similar architecture, one big stack, crew, lander, return vehicle, supplies, all launched from Earth and pushed out in one shot, the numbers explode. Now you are not talking about hundreds of tons in low Earth orbit, you are talking about thousands of tons. You need a large interplanetary habitat, more fuel, more consumables, more redundancy, and a whole Mars descent vehicle waiting for you. Modern heavy-lift rockets like SLS or Starship aim to put more than 100 metric tons into low Earth orbit per launch, over 220,000 pounds. That is powerful, but if your Mars mission needs something on the order of 1,000 tons or more in orbit, you are suddenly not doing one launch, you are doing many. You may have to build your Mars ship in orbit, piece by piece, docking modules together. Or you launch tankers whose only job is to refill the main spacecraft's tanks while it waits in orbit. That means a Mars mission is not a single shot, it is a campaign of launches. Each launch has to succeed, the timing has to line up, the refueling has to work, the orbital assembly has to be safe. One Mars mission turns into a whole fleet operation just to get the starting mass into place before you even leave Earth's gravity well. Underneath all of this, there is a deeper constraint. You are working against gravity wells, and each one charges a different price. So the next question is, how much does gravity itself contribute to making Mars harder than the Moon? Earth's surface gravity is about 9.8 meters per second squared, which we call 1g. That is what you feel right now. To climb out of that gravity well and reach orbit, you burn a huge amount of chemical energy. Mars has a lower surface gravity, about 3.7 meters per second squared, roughly 0.38 g. The Moon is even lower, about 1.62 meters per second squared, around 0.17 g. Lower gravity means it is easier to take off from that body. You need less delta V to reach orbit from the surface. That is why the lunar ascent stages in Apollo look so small and light. The lander that came off the Moon did not need enormous engines or giant tanks, because climbing out of 0.17 g is much cheaper than climbing out of 1 g. On Mars, taking off is harder than on the Moon, but easier than from Earth. That helps, but only on one side of the trip. You still had to pay the full Earth gravity price to launch every kilogram of spacecraft, fuel and cargo off our planet's surface in the first place. The lower Martian gravity does not erase that initial cost. You still need to climb out of Earth's deep gravity well with everything you want to use on Mars. So when people say, why don't we just add more fuel and push harder? The answer is, the rocket equation punishes that idea quickly. Every extra kilogram of fuel you put on top needs extra fuel under it to lift it. That extra fuel below also needs structure, tanks, stronger engines, more guidance, which adds more mass, which then needs even more fuel. If you keep stacking propellant, there is a point where your rocket is almost all fuel and tank, with a tiny useful payload on top. The mass ratio becomes ridiculous. Mars missions push right up against this non-linear curve. That is why there is so much talk about in situ resource utilization, or ISRU. Instead of hauling all your return fuel from Earth, you mine water ice on Mars, split water into hydrogen and oxygen, and react Martian carbon dioxide with hydrogen to make methane and more oxygen. You build a fuel plant on Mars so the return vehicle can be filled there. ISRU is not a cool bonus feature. It is a way to escape the worst of the rocket equation. It lets you shrink the mass you need to launch from Earth, which shrinks the number of launches, which shrinks cost and risk. Without tricks like that, the numbers for a fully Earth-supplied Mars mission start to look unmanageable. And here is the hard part. All of this painful rocket math, all of these fleets of launches, all of this clever fuel chemistry only solve one part of the problem, getting a big, heavy ship to arrive at Mars with enough capability to matter. Because after you have fought gravity and fuel and mass and cost, you still have to answer the next brutal question. How do you take that massive, fragile stack and actually land it safely on a planet whose atmosphere is too thin to help you and too thick to ignore? Landing is where Mars stops being just far away and starts actively trying to kill your mission. Getting there is one problem, but slamming into a planet at several kilometers per second and trying to survive the arrival is a completely different layer of difficulty. The scary part is, the moon actually spoiled you here, because it made landing look simpler than it really is. On the moon, the rules are harsh but clean. There is basically no atmosphere, just vacuum. When you come down toward the surface, you do a powered descent. You point your engines down, you burn fuel, you control your speed and your angle with guidance computers and thrusters, and you ride thrust all the way to the ground. The only forces you really care about are gravity pulling you down and your engines pushing you up. No lift, no drag, no turbulence. The math for that kind of landing is ugly in terms of fuel, but predictable. If you know your mass, your engine performance, and the moon's gravity, about 1.62 meters per second squared, roughly 0.17 g, you can calculate how much propellant you need to slow down from orbital speed to zero at the surface. Apollo's lunar module did exactly this. It came down on its own rocket plume, kicking up dust, but following a plan that mostly involved balancing thrust against gravity. So here's the key question. What happens when you try to do this on a world that has just enough air to mess you up, but not enough air to carry your weight? Mars has an atmosphere, but it is thin. The surface pressure is only about 0.6% of Earth's. That's similar to the air you'd find 30 to 35 kilometers above Earth's surface, over 100,000 feet up. It is not vacuum, but it is not normal air either. When a spacecraft hits the top of that atmosphere at entry speeds of around 5 to 7 kilometers per second, roughly 11,000 to 15,000 miles per hour, the thin gas still compresses and heats violently. You get intense aerodynamic heating that demands a serious heat shield, just like a capsule returning to Earth. But as you go deeper, the air is too thin to give you the kind of drag you get on Earth. Parachutes can help, but only so much. For a small lander or a rover, the combination of a heat shield, then a parachute, then some rockets is enough to bring it down. For a large human lander, the atmosphere is in an awkward middle zone, thick enough that you must respect it, thin enough that it will not do the full job of slowing you down from supersonic speeds. So you're stuck with a paradox. If there were no air, you'd just plan a clean powered descent like on the moon. If there were thick air like Earth, you'd rely heavily on drag and parachutes. Mars sits between those cases, forcing you to deal with the complications of both, but the full benefit of neither. We already have proof of how hard this is, even for robots much smaller than a crewed ship. Rovers like Curiosity and Perseverance did not just pop down with one simple technique. They used a chain of systems, a heat shield for the initial entry, a supersonic parachute to slow down further, then a powered descent stage with retro rockets, and finally a sky crane that lowered the roughly 1-ton rover, about 2,200 pounds, on cables to the surface. That entire sequence, from hitting the atmosphere to touching down, takes around 7 minutes. Engineers call it 7 minutes of terror because once it starts, you cannot interfere. The radio signals between Earth and Mars take between 4 and 24 minutes to travel one way depending on where the planets are. By the time you see the start of entry on your screens on Earth, the rover has already either landed or crashed. It has to make decisions autonomously, when to drop the heat shield, when to deploy the parachute, when to fire the rockets, when to cut the cables. Now scale that up in your head. Curiosity and Perseverance are about 1 ton. A human lander is not 1 ton. It could be 20 to 40 tons, and that's a conservative range, 20,000 to 40,000 kilograms, around 44,000 to 88,000 pounds. The forces, the heating, the structural loads all go way up. You have to land not a car-sized rover, but something closer to a small building. The same choreography has to work, but now the stakes are lives, not hardware. If parachutes are part of the answer, why not just build bigger ones and keep scaling up? The problem is, parachutes do not scale nicely forever. The drag force they create depends on the area of the canopy and the square of the velocity. That sounds like just make it big, but reality gets in the way. Materials can only handle so much stress before they tear. Supersonic airflow creates shock waves and violent, unsteady forces on the fabric. There is a practical limit to how large and how heavily loaded a parachute can be, especially when you are deploying it at several times the speed of sound. At Mars's low air density, a parachute that would easily slow a heavy vehicle on Earth might barely be enough for something much smaller. That is why an Earth-style, parachute all the way down and then a short rocket burn strategy does not work for very massive landers on Mars. The air just does not give you enough braking force in the time and altitude you have. So engineers are pushed towards solutions like supersonic retropropulsion, which means firing rocket engines while still going at very high speeds in the thin Martian air. That creates a whole new set of problems. The rocket exhaust interacts with the airflow around the vehicle, changing the pressure distribution. Shock waves form and move in complex patterns. The hot exhaust can recirculate and heat parts of the vehicle you do not want heated. You have to understand all of that and control it so the vehicle stays stable instead of flipping or breaking up. This is being explored using data from reusable boosters that land back on Earth, but Mars adds different air density, different gravity, and different entry profiles. You are basically designing a flying, supersonic, high-temperature control problem where your safety margins are thin and your ability to test full-scale on Earth is limited. And we have not even talked about how big the thing you're landing actually is. A human-rated Mars lander might mass 20 to 30 metric tons, about 44,000 to 66,000 pounds, before you even count cargo. Some concepts go higher. That is in the same mass range as small jet airliners or big trucks. You're trying to bring that down onto a surface that has rocks, slopes, loose dust, and unknown small hazards, in an atmosphere that is too thin to let you float and too thick to ignore. Your guidance system has to scan the ground, avoid boulders, adjust its trajectory, and throttle engines in real time. Human pilots cannot fly it down in the moment because of the communication delay. By the time someone on Earth says correct to the left, the lander has already either corrected or smashed. So you need onboard autonomy that you trust completely on the first few tries, when failure means losing a crew and possibly setting back Mars exploration for decades. So when you look at entry, descent, and landing on Mars, you are not just dealing with one difficulty, you are dealing with a stack of them. Thin atmosphere, high entry speeds, limited parachute usefulness, complex rocket airflow interactions, Heavy vehicles, rough terrain, and no real-time control from Earth. The Moon let you get away with a clean-powered landing problem in vacuum. Mars forces you into a messy hybrid regime that we have only just started to master with small robots. And here's the next uncomfortable question you have to face. Even if you somehow solve all of that, and you can reliably drop heavy human landers on Mars, what exactly are those humans sitting in for months and years between launch and landing and the trip home, while cosmic radiation and solar storms are hitting them with energy their bodies were never designed to handle? You live your whole life under a shield you never see, so the real question is, what happens when you leave that shield behind for years instead of days? On Earth, you sit inside Earth's magnetic field, the magnetosphere, and inside bands of trapped particles called the Van Allen belts. Together, they deflect a lot of charged particles from the Sun and from deep space, so the radiation dose at the surface stays low, just a few millisieverts per year in most places. Apollo did step outside that protection, but only briefly. Those missions cut through the Van Allen belts, then spent a few days in open space on the way to and from the Moon. Measurements showed doses around 1 to 2 millisieverts per day during the journey, and total doses on the order of 11 millisieverts for a full mission. That's not nothing, but as a one-off hit, it's not catastrophic. For comparison, a CT scan might give you a few millisieverts. Apollo astronauts basically took a handful of CT scan level hits spread over a week and a half. For a small number of people one time, that was considered acceptable. So here's the key issue. If a few days outside the shield is manageable, what happens when you stretch that exposure from days to many months, or even years? Robotic missions heading toward Mars have already given us hard numbers. The Curiosity rover carried a radiation detector during its cruise. It measured roughly 1.8 millisieverts per day in interplanetary space, once the spacecraft was out from under Earth's protective bubble. Over a 6-month trip, about 180 days, that adds up to something like 320 millisieverts on the way out, just from the cruise phase. Now double that for the return trip, and you are already in the 600 to 700 millisievert range, without counting time spent near or on Mars. Add surface exposure, plus any extra time in transit if your trajectory is longer, and you start to approach or even exceed typical career limits that agencies like NASA set for astronauts over their entire working lifetime. Those limits exist because above certain totals, the risk of cancer and other long-term health problems climbs sharply. So you're not dealing with a quick burst of radiation like in Apollo, you're dealing with a slow, steady hammer, hitting the crew every single day. That leads to the next question. What exactly is slamming into the ship out there, and why is it so hard to stop? The space between planets is full of two main kinds of radiation threats. The first is galactic cosmic rays, or GCRs. These are high-energy particles, mostly protons and heavier nuclei that come from outside our solar system, accelerated by events like supernovae. They are moving at speeds close to the speed of light and can cut through matter very deeply. To reduce their effect significantly, you need a lot of shielding, often talked about as tens of centimeters of water, or plastic-like materials such as polyethylene. The second threat is solar energetic particles, SEPs, from the Sun. These come in bursts during solar flares and coronal mass ejections. When one of these events happens, the flux of particles can spike drastically over a few hours to a few days, raising radiation doses to dangerous levels very quickly. If a crew is caught without enough shielding during a strong solar storm, they could receive a dose that causes acute radiation sickness, not just long-term cancer risk. So you have a constant background of GCRs, which are hard to block but steady, and unpredictable SEP events that can suddenly slam you with extra dose. That combination means you need a strategy for both slow, chronic exposure and sudden spikes. That makes the next question obvious. If radiation is this bad, why not just build the ship like a bunker and bury the crew in thick shielding? In theory, you could wrap your spacecraft in enough material to cut doses way down. In practice, the mass penalty is brutal. To reduce radiation significantly, you might want shielding equivalent to 20 to 30 grams per square centimeter. Translated into real hardware, that can mean tens of tons of water plastic, or other hydrogen-rich materials distributed around the living areas. Water is great because you already need it, and it has good shielding properties, but lifting that much extra mass from Earth's surface costs you heavily in rocket size and fuel. Every ton of shielding you add has to be accelerated to orbit, then to Mars, then slowed down, then brought home or left behind. That ton did not go to food, equipment, or science gear. It's just sitting there as a passive barrier. You cannot simply say we'll double the shielding, because doubling might mean adding many more launches, more complexity, and more cost. So engineers look for compromises. One idea is a storm shelter, a compact safe room in the ship surrounded by water tanks, food stores, and other supplies. Most of the time, the crew lives in a lighter, less shielded section, taking the chronic GCR hit. When a solar storm warning comes in, they move into the shelter for a few hours or days to ride out the spike from SEPs. This helps deal with the worst events without requiring the whole spacecraft to be a giant armoured capsule. But it does not eliminate the long-term GCR problem, because you can't stay inside a tiny bunker for an entire 900-day mission. So you might think, alright, deep space is rough, but at least once you land on Mars, the planet itself should shield you and give you a break, right? The reality is harsher than that. Mars does reduce radiation compared to free space, but not enough to call it safe. The thin atmosphere and weak magnetic field cut some of the dose. Measurements from surface missions show around 0.6 millisieverts per day at the ground on average. That is lower than the 1.8 millisieverts per day you see in deep space, but it is still about 20 times the dose you'd get on Earth's surface. Over a year, that stacks up fast. You're basically getting something like a CT scan level dose every few days. For short visits, maybe that is tolerable. For multi-year stays, it adds a big chunk to the lifetime risk for each crew member. To bring that down, long-term habitats may not be simple domes sitting on the surface. They might need to be buried under several meters of Martian soil called regolith, or even built inside lava tubes or under layers of ice. That regolith becomes your shielding, slowing and absorbing incoming radiation before it hits the living space. But digging into Mars, moving tons of dirt, building underground or under ice, all of that means heavy machinery, power systems, maintenance, and extra failure modes. Radiation is pushing you toward more complex infrastructure from day one, not just land a habitat and walk in. So when you put it all together, the invisible storm of radiation turns a Mars mission into a long negotiation with physics. Every day in transit and every day on the surface adds to a dose you cannot reset. You're constantly trading between more shielding, which costs mass and fuel, and more risk to the crew's health, which costs safety and long-term viability. And that leads straight into the next problem, one that ties into everything you've just heard. Because it's not enough to shield a crew from radiation for 900 days. You also have to feed them, hydrate them, give them air, and keep all those systems running with almost no resupply. So the question becomes, how do you scale life support from a 10-day sprint like Apollo to a multi-year marathon on the way to and from Mars, without the whole system collapsing under its own complexity? How do you keep people breathing for years in deep space when the longest thing you've really done before is a few days? That's the gap between Apollo and Mars, and it's not a small upgrade, it's a total change in what life support even means. Apollo was a sprint. 3 people, about 8 to 12 days, that's it. Oxygen, water, CO2 scrubbers, batteries, all deployed for something closer to a camping trip than a permanent move. If you add it up, that's roughly 30 person days of life support, 3 people times around 10 days. You can afford to be wasteful in that regime, carry oxygen in tanks, carry water in bags, toss out waste. The systems only have to behave themselves for a week and a half, and after that the crew is back under Earth's atmosphere and gravity. Now compare that to Mars. A realistic mission is more like 900 days away from home, maybe more. And you're not flying 3 people, you're probably flying 4 to 6. Take the lower end, 4 people for 900 days, that's 3,600 person days. Go to 6 people, and it's 5,400 person days. Even if you just say about 1,000 person days to be conservative, you're still more than 30 times the total life support load of Apollo. That's not a longer camping trip, that's turning your spacecraft into a tiny closed world that has to run without a break for years. So the next question hits immediately. Can you keep doing life support the old Apollo way, or do you have to change the whole philosophy? Apollo mostly used open-loop systems. You start with tanks of oxygen and water, you use them, you vent or store waste, and you don't expect to get most of it back. That's fine for 10 days. For 900 days, that is a logistics nightmare. For Mars, you're forced toward closed-loop life support, where you recycle as much as possible. You scrub CO2 out of the air and turn it back into oxygen. You capture water from humidity, sweat, and urine, clean it and drink it again. You aim for recycling efficiencies above 90 to 95% for both air and water, because anything less starts to blow up your mass budget. We already do pieces of this on the ISS. The station reclaims water from urine, from the air, from equipment, and turns it back into drinkable water. Oxygen can be generated by splitting water molecules. That system works, but it gets constant attention, regular maintenance, and resupply flights with filters and spare parts. Scaling that to a Mars mission means taking a technology that works in a serviced lab and expecting it to behave as your only lifeline, far from any help, for years. So what happens if you say, forget the recycling complexity, we'll just carry everything we need from Earth? The numbers get ugly, fast. Take simple round numbers. Say each astronaut needs about 5 kilograms of water per day, around 11 pounds. That includes drinking, basic hygiene, and food preparation. They also need about 0.84 kilograms of oxygen per day, roughly 1.9 pounds for breathing. For 4 people over 900 days, water alone becomes 5 kilograms times 900 times 4. That's about 18,000 kilograms or 18 metric tons, close to 40,000 pounds. Oxygen becomes 0.84 times 900 times 4, a bit over 3,000 kilograms, about 3 metric tons, around 6,600 pounds. Add those together and you're already past 46,000 pounds of just water and oxygen. No food yet, no packaging, no spare parts, no tools, no science gear, no habitat structure, no radiation shielding. And remember, every extra ton has to be launched out of Earth's gravity well, accelerated to Mars, slowed down, and maybe brought back. This is why people obsess over recycling rates. Without aggressive recycling, the consumables alone crush the mission. Even if you do recycle, the next problem is not just how efficient the loop is, but how reliable it is. On the Moon, if a water system failed, you were only a few days from home and you had backup tanks. On Mars, any major life support failure is existential. There is no quick resupply, no rescue ship coming next week, no evacuation route. If your CO2 scrubbers fail and you can't fix them, you suffocate. If your oxygen generator fails and you can't repair it, you run down your reserves and die. If your water recycler breaks and you don't have parts, you run out of clean water, and that's it. That changes how you think about hardware. It's not enough to have one CO2 scrubber, you need redundant ones. Not enough to have one oxygen generator, you need backups and maybe different types. Pumps, valves, filters, electronics, all need spares. You care about mean time between failure the way you care about your own lifespan, because for a Mars crew, those numbers are almost the same thing. Every extra moving part is another chance of a breakdown in the middle of nowhere. You can feel where this is leading if closed-loop mechanical systems are barely enough and brutally complex. Is there any way to let biology carry some of the load? Long-term, people talk about bioregenerative life support. Instead of just machines, you use living systems, algae reactors that turn CO2 into oxygen, plants that scrub the air, grow food, and help manage humidity, small greenhouses that close the loop more like an ecosystem than a factory. In theory, a well-designed bioregenerative system can recycle air, water, and nutrients with very high efficiency and give the crew fresh food and psychological benefits at the same time. But biology is not as predictable as a metal box with a pump inside. Plants need stable temperatures, controlled lighting, specific nutrient mixes. They react to radiation, to microgravity, to partial gravity like Mars's 0.38 g, in ways we do not fully understand yet. Algae bioreactors can crash if conditions drift. Microbes can overgrow or die off. You can't reboot a greenhouse the way you reboot a computer. Experiments on Earth and on the ISS are still ongoing, and we are far from having a fully proven, multi-year, self-regulating biological life support system. So right now, the tech that would make Mars feel truly livable, not just survivable, is still mostly experimental. For the first Mars cruise, life support will likely be a hybrid, heavy mechanical recycling with maybe some small-scale biological help running at the edge of what we know how to build and maintain. And even if you get that right, even if your air stays breathable and your water stays drinkable for 900 days, you still haven't solved what waits outside the habitat walls, because the second you step out the airlock, you're in a place that is not just cold and dusty, it's a whole new environment, with lower gravity, brutal temperatures, thin CO2 air, and dust that can attack your body and your hardware at the same time. So the next question is simple and brutal. What does it actually mean to live and work on a planet that looks like a desert, but behaves like nothing you've ever experienced on Earth? You hear people talk about Mars like it's just a colder version of a desert on Earth. Red rocks, big sky, dust everywhere. Throw on a better spacesuit and you're fine. That picture is wrong. The real problem is that almost every normal thing your body and your hardware expect from a planet is either missing, twisted, or pushed into an unknown zone on Mars. Start with gravity, because your body is built around it, and Mars does not match anything you've actually tested for years. On Earth you live at 1G. In orbit, astronauts float at effectively 0G. We have a lot of data on those two regimes. We know that at 0G, bones lose density fast, muscles waste away, the heart and blood vessels adapt in ways that cause trouble when you come back down. The Moon has about 0.17G, Mars has about 0.38G. For 0.17G, we only have a few days of Apollo data, not years. For 0.38G, we have basically nothing for humans. So you land a crew on Mars and you're asking them to live at 0.38G for more than a year, then come back to 1G on Earth. Does that lower gravity slow down bone loss compared to 0G, or just change the pattern? Do muscles stabilize at a new, weaker baseline or keep degrading? Does the heart stay strong enough to handle emergency work? Lifting, running back to the habitat in a suit if something fails? No one knows yet. You're running a medical experiment on bodies that evolved for Earth. In a gravity field we've never kept humans in for that long. Then you add temperature to the stack. Mars is cold, but it's not just wear a thicker jacket cold. Typical surface temperatures hover around minus 60 degrees Celsius, about minus 76 Fahrenheit. Near the equator, on a good day at noon, you might see 20 degrees Celsius, around 68 Fahrenheit, something that feels almost comfortable. But after the sun sets, temperatures can drop below minus 100 Celsius, around minus 148 Fahrenheit. That's not occasional, that's normal. On the Moon you get two main states, blazing hot in daylight, brutal cold at night, and you can design systems around that cycle. On Mars you get gradients all the time, between day and night, between seasons, between latitudes, with thin air that can't hold heat and dust that changes how sunlight and infrared energy move around. Hardware, suits, seals, vehicles, all have to survive repeated thermal cycling, heating and the cooling, with materials shrinking and expanding differently. A small crack in a radiator or a tiny leak in a line can start as a nuisance and turn into a fatal failure during one of those deep drops. Now look at what you're breathing, or rather, what you absolutely cannot breathe. Mars's atmosphere is mostly carbon dioxide, roughly 95% CO2. The average surface pressure is about 600 pascals. That's around 0.087 pounds per square inch. For comparison, Earth's surface pressure is around 101,000 pascals, about 14.7 pounds per square inch. The air on Mars is closer to what you'd get 30 to 35 kilometers above Earth's surface. Your lungs are useless there without a pressure suit or a habitat. But at the same time, that CO2 soup is not just a threat, it's a resource. You can split CO2 into oxygen and carbon monoxide. You can combine CO2 with hydrogen, for example from water, to make methane and water again. That gives you a path to rocket fuel and breathable oxygen using local materials. So your atmosphere is both a suffocation hazard and a feedstock for your factories. You need compressors, reactors, storage tanks, and control systems that can suck in that thin air, process it, and keep working for years in dust, cold, and radiation. If they fail, you don't just lose a science experiment, you lose your oxygen and your return fuel. And then there's the dust, which is not a minor detail, it's a central enemy. Martian dust grains are extremely small, often under 10 microns, in the same size range as cigarette smoke particles. That means they float easily, get into everything, and hang in the air for a long time. They stick to surfaces through electrostatic charge, cling to suit fabric, coat visors, blind cameras, and work their way into mechanical joints. On the Moon, Apollo astronauts reported that lunar dust was like ground glass, abrasive and sharp. It tore up suit joints and clogged mechanisms after only a few spacewalks. Mars takes that mechanical problem and adds chemistry and an atmosphere. Analyses suggest Martian dust may contain perchlorates, reactive chemicals that can interfere with thyroid function and cause other health problems if inhaled or ingested over time. So now your dust is not just scratching your seals, it's also potentially toxic to your crew. You need airlocks that clean dust off suits, filters that can handle ultrafine particles, suit materials that don't fail after dozens or hundreds of excursions, and procedures that keep this stuff out of your lungs and your food. Every time someone goes outside and comes back in, they're not just bringing back samples, they're trying not to bring back invisible, dangerous grit. Finally, put this dust into motion on a global scale, and you run into one of the biggest threats to your power and your visibility: planet-wide dust storms. Every few Martian years, dust storms grow and merge until they cover huge fractions of the planet, sometimes wrapping all the way around. The dust in the air increases atmospheric opacity, meaning less sunlight reaches the ground. Your solar panels don't see a gentle reduction, they can see their output plunge to a small fraction of normal for weeks. This isn't theory, we've already watched it happen. The Opportunity rover, which ran far longer than planned, finally went silent after a massive planet-encircling storm cut sunlight so much that its solar panels could not recharge the batteries. It went to sleep and never woke up. Now scale that problem up to a human outpost that depends heavily on solar power. If you rely only on large solar arrays, you can't assume bigger is safer. In a global dust storm, you might get almost no usable power no matter how big your array is, so you need big battery banks, energy storage that can carry you through days or weeks of low light, and most likely nuclear backup, small fission reactors that don't care about the weather. You also need to design for dust-covering panels, scraping mechanisms to clean them, and safe modes for equipment when the sky goes dark for a long time. So put all of this together: an unknown gravity regime for human health, temperature swings that stress every material you brought, an atmosphere that kills you if you breathe it, but has to run your oxygen and fuel plants, dust that attacks your suits, your machines, and possibly your body, and storms that can shut down your main power source for weeks. That's what surface environment really means on Mars. And even if you manage to survive all of that, even if your outpost is tough enough to handle gravity, cold, air, dust, and storms, there is another layer that turns Mars from hard to unforgiving. When something goes wrong and you want help, Earth is not a quick call away. Signals crawl across tens of millions of kilometers, turning every question into a long pause. So the next problem is simple to state and nasty to solve. How do you operate when Houston, we have a problem, turns from a live conversation into a delayed message that might come back too late to matter? You can pick up your phone and talk to someone on the other side of Earth with barely any delay. So why does talking to Mars suddenly feel like sending mail by ship instead of having a call? The brutal truth is, once you leave the Earth-Moon zone, even the speed of light starts to feel slow. The Moon sits about 1.3 light seconds away. That means a radio signal, which travels at light speed, takes roughly 1.3 seconds to go from Earth to the Moon and 1.3 seconds to come back. During Apollo, that delay was noticeable, but it was small enough that you could still talk to mission control in a way that felt live. You say something, wait a beat, you hear the reply. It's like a slightly laggy phone call, not a different mode of communication. Because of that, Apollo crews could lean heavily on Earth. They could describe a problem, pause, and get instructions. Ground controllers could watch the data in real time, catch issues early, and walk the crew through fixes step by step. The system was crew plus mission control acting almost as one unit, tied together by a delay that was annoying but manageable. Now shift that same model out to Mars, and the whole thing breaks. Mars is not 1.3 light seconds away. Depending on the orbits, it's at about 4 to 24 light minutes away. That means a one-way radio signal can take anywhere from 4 minutes at the very best alignment to almost 24 minutes at the worst. Round trip, you're looking at something like 8 to almost 50 minutes for a full back and forth exchange. So here's the key question. What does Houston, we have a problem, even mean when the answer comes back half an hour later? By the time a crew on Mars asks, what do we do? They've already lived through the crucial part of the emergency. A leak, a fire, a power spike, a suit failure. These are minute scale events, not hour scale. Waiting for mission control to respond would be like freezing during a car crash and asking someone on another continent how to steer. The event is over before the advice arrives. That delay forces a total shift in how you think about operations. Autonomy stops being a nice extra and becomes mandatory. A Mars crew has to behave less like airline pilots in constant contact with a tower, and more like submarine commanders deep underwater, cut off from instant help. They need systems on board that can diagnose their own health, flag anomalies, and propose fixes without waiting for Earth. They need procedures built around the assumption that in a serious fault, no one on Earth will tell them what to do in real time. That's where heavy onboard computing and yes, AI assistance comes in. You need software that can look at hundreds of sensor readings, detect patterns that humans might miss in the moment and say, you probably have a leak here, close this valve, reroute power like this. Even our robots on Mars already live this way. Rovers like Perseverance receive high-level plans, things like drive to that rock, take a sample, send pictures, but the detailed pathfinding, avoiding rocks and holes, reacting to wheel slip, that's handled on board. The robot has to commit to actions when there's no chance to ask Earth about every little bump. So autonomy solves the moment-to-moment problem, but it doesn't remove another big limitation, the pipe you're trying to send data through. You're running a whole mission, maybe eventually a whole outpost, through a link that will never feel like modern broadband. High-gain antennas can push data at tens of megabits per second under good conditions, but good conditions depend on distance, antenna alignment, available relay satellites, and power. Sometimes that bitrate drops, sometimes you're using orbiters as relays, sometimes geometry is bad and you have to accept slower, noisier links. Compare that to a 1 gigabit per second fiber connection on Earth. Down here, you can stream 4K video to multiple devices without thinking about it. On Mars, sending a batch of high-resolution images, engineering logs, and science results can be a major part of your daily plan. There will be periods where Mars is behind the Sun from Earth's point of view, or where local terrain blocks direct line of sight to relay satellites. In those times, your outpost may be partially or completely cut off for hours, maybe longer. You can buffer data, you can schedule transmissions, but you cannot press a button and expect instant feedback. Every status update is store and forward. Every command upload is timed and queued. Technically, that's frustrating, but manageable with good planning. The deeper impact shows up in a place people tend to underestimate: the crew's headspace. This delay isn't just a network problem, it's a psychological one. On the Moon, the crew knew Earth was listening almost in real time. If something felt wrong, they could say it out loud and hear a human voice come back moments later. On Mars, every message is a time capsule. You record a video for your family, send it, and they see a version of you that is already several minutes old. They reply, and you watch their answer knowing that whatever they're reacting to happened long ago in your local time. There is no live conversation, no "Are you okay?" followed by an immediate "Yeah, I'm fine." You also don't get live sports, live news, or real-time social media. Everything is delayed, buffered, curated, and delivered when bandwidth allows. your sense of being part of Earth's ongoing story gets weaker. Your emotional world shrinks down to the handful of people inside your habitat and the delayed messages on your screen. When something scary happens, Mission Control can send long, thoughtful guidance, but they cannot be there with you at the pace your fear is actually unfolding. So communication with Mars is not just about bigger antennas and better compression. It forces you to design missions where Earth is more like a distant advisor than a control center. The crew has to be more trained, more cross-skilled, more independent. The software has to be smarter, the procedures more robust, and the psychology support has to expect long gaps with no fresh contact. And once you accept that you can't lean on live support from Earth, a new, harsher requirement appears. If you can't get real-time help and you can't get frequent resupply, then more and more of what you need has to be produced, repaired, and managed locally on Mars itself. That leads to the next question with even higher stakes. How do you move from bring everything and hope it lasts to build a working mini-civilization on another planet, with factories for fuel, air, water, and power operating in that hostile environment? Here's the uncomfortable truth about Apollo that people don't say out loud. It was never about living somewhere else, it was about proving you could visit and come home. On the Moon, that was enough. On Mars, that mindset collapses instantly. On the Moon, Apollo could treat the surface like a short camping trip. You bring all your gear, you bring your air, your water, your food, your tools, you stay a little while, you leave some experiments, and then you go home. The longest stay, Apollo 17, was about 75 hours on the surface, a little over 3 days. You didn't need a mine, you didn't need a chemical plant, you didn't need a power grid that could survive years of operation. You could pack almost everything in one mission stack and accept that nothing had to work for very long after you left. So here's the key shift. On Mars, that bring everything, leave footprints model fails the moment you want more than a single heroic landing. On Mars, if you want anything close to sustainable, you have to stop acting like a visitor and start acting like a builder. That's where in situ resource utilization, ISRU, stops being a buzzword and becomes your main strategy. Instead of hauling all water, all oxygen, all fuel from Earth, you tap Mars itself. You mine ice for water, you split that water into hydrogen and oxygen. You take the CO2 in the Martian air and react it with hydrogen through the Saboteur process to make methane fuel and more water. None of that is a little side project. It means drills that can work in cold, dusty ground. It means reactors, compressors, pumps, thermal control, large storage tanks, and maintenance robots or humans in suits constantly checking valves and filters. You're not just landing a sleek spaceship, you're landing an industrial park that happens to be on another planet, and it has to run continuously, not for a weekend, but for years. So the next question becomes obvious. What's the first resource you go after when everything is trying to kill you and your mass budget is already screaming? Water ice is the first big prize. Orbiters and landers have already found strong evidence of water ice in the polar caps and as buried layers in mid-latitude regions. For you, water is ridiculously valuable. You drink it. You use it for hygiene and food. You feed it to plants if you grow any. You split it into oxygen for breathing and hydrogen for fuel. You can even park water around habitats as part of your radiation shielding. But here's the problem. There is ice on Mars is not the same as you can easily use it. You need deposits that are close to the surface, not tens of meters down. You need those deposits to sit at latitudes where humans can actually live and work, not at the most extreme poles. You need the ice to be clean enough that your systems can handle it without constant clogs and corrosion. Finding ice that is shallow, accessible, and located in a place that gets decent sunlight is a real challenge. That requires detailed mapping from orbit, ground truth from landers, and a lot of scouting before you even think about a permanent base. Once you're mining and processing resources, you run into the next brutal constraint: power. None of your factories, habitats, or drills run on hope, they run on watts. At Mars's distance, about 1.5 times farther from the Sun than Earth, sunlight is only around 43% as strong as it is here. A 1 kilowatt solar panel on Earth, under good conditions, might give you roughly that rated power. On Mars, to get the same output, You might need more than 2 kilowatts worth of panels installed, because each panel is getting less light and you have to factor in dust and aging. And that's on a clear day. Dust buildup on panels slowly drags your power down. Then dust storms come, local or global, and your output can crash. So you can't just say, we'll use solar and be done. You need a mix: large solar arrays for normal operations, energy storage like big battery banks or other storage tech, and then a backbone that doesn't care about sunlight at all. That's why small fission reactors, kilowatt-class, kilo-power style units, are taken very seriously. A compact reactor can deliver steady power day and night through dust storms, through winter, without caring about the sky being clear. But nuclear power brings extra complexity, transport issues, safety concerns, and long-term waste handling, all of which you now have to solve on another planet. Even if you know what resources you want and what power system you like, you still haven't answered the practical question. Do you risk human lives on the very first attempt, or do you build a safety net first? A cautious strategy looks like this. You don't send humans first, you send cargo ships. Uncrewed landers touch down with power systems, propellant plants, and inflatable or rigid habitats. Robots deploy solar arrays, hook up cables, start the ISRU reactors, and begin making oxygen and methane from the Martian atmosphere and local water. You let this setup run for a Martian year, about 687 Earth days, nearly 2 Earth years. During that time, you watch from Earth. Do the systems keep working? Do the reactors clog? Do the lines freeze? Does the power hold up through storms? Do the tanks actually fill with enough return fuel? Only when you see that these machines can operate mostly on their own, in real Martian conditions, do you commit a crew. When they arrive, the return ship's fuel is already waiting. The habitats have already cycled through at least one harsh season. The power grid has already proven it can ride out dust storms. That is a much safer way to do it, but it also means a choreography of missions over many years, with multiple landings, precision targeting, and coordination that Apollo never had to attempt. So now you're not talking about one big mission, you're talking about a campaign, with cargo flights, robotic miners, chemical plants, power stations, maintenance bots, all working before humans set foot there. It starts to look less like exploration and more like building a remote industrial zone in one of the harshest environments you can find. And even after you've done all this, after you've built factories in the dust and lit up a small power grid on a hostile world, you still have one more brutal constraint you can't engineer your way around easily: the human body itself. Because everything you build, every drill, every reactor, every habitat, is ultimately there for one fragile system you can't redesign from scratch. A human in microgravity for months, then in partial gravity for years, then back to 1G on Earth. So the next hard question is this: what happens when you push human biology through years of microgravity, radiation, partial gravity, and stress, with no chance to come home until the mission is over? How much can a skeleton, a heart, a brain, and an immune system really take before the mission breaks the crew, even if the hardware works perfectly? You can engineer rockets and habitats, but you can't swap out a human skeleton halfway to Mars. So what actually happens to your body when gravity disappears for years instead of months? This is where the mission stops being just a hardware challenge and turns into a direct attack on your bones, muscles, heart, and nervous system. Start with bone, because bone does not care that you're an astronaut. It responds to load and only to load. On Earth, at 1G, your skeleton is under constant pressure. Every step, every jump, every time you stand up, your body says, "We need this structure." In microgravity, that signal drops off a cliff. On the ISS, without countermeasures, astronauts can lose around 1 to 2% of bone mass per month in key load-bearing areas like hips and spine. Stretch that to 6 months in orbit and you're looking at roughly 6 to 12% bone loss. That's the kind of change you'd worry about in an elderly patient on Earth, happening in half a year to a healthy, trained astronaut. We fight this with intense exercise programs and sometimes medications that slow bone breakdown. Treadmills with harnesses that pull you toward the belt, resistance machines cycling, all trying to trick your bones into thinking they're still carrying weight. For a Mars mission, you're not just talking about 6 months in microgravity and done. You might do 6 to 9 months outbound, then more time on the surface, then another long trip back. The total exposure pushes up toward 2.5 years. You are stretching these countermeasures right to the edge of what we know they can handle. And if bone density keeps dropping even slowly, fracture risk, spinal problems, and long-term disability all start to climb. Now look at muscles and the heart, because they follow the same rule. No load, no reason to stay strong. In microgravity, the muscles in your legs, hips, and back don't have to fight gravity to hold you up. They atrophy. They shrink. Even if you train, you're fighting against a missing force field that used to shape your entire daily life. The heart changes too. On Earth, it works against gravity to pump blood up from your legs to your chest and head. In microgravity, that pressure difference collapses. Fluids shift toward the upper body, faces puff up, legs thin out. The heart remodels to this new workload, and when you eventually go back to a gravity field, it suddenly has to do more again. So picture the sequence. You spend months in microgravity on the way to Mars, doing your best with exercise, but still losing some strength and endurance. Then you land on Mars at 0.38 G. That's less than Earth, but far more than zero. You're now asking a deconditioned body to walk in a spacesuit, lift tools, carry equipment, deal with emergencies, all in a gravity level it hasn't felt in months. You're not starting from full strength. You're starting from a compromised state, and you're relying on everything going mostly right. Then there's the part that's even less understood. What happens to your whole biology over a full Mars mission? Not just your bones and muscles, but your brain, immune system, and microbiome. Space medicine as a field is still young. So far, only a few dozen people have spent more than a year in space total, and those experiences are mostly in low Earth orbit, still partly protected by Earth's magnetic field, with constant medical monitoring and resupply. A full Mars mission is close to 2.5 years away from home, much of that in deep space with high radiation and constant stress. We have some hints. We know vision changes can happen, with fluid shifts affecting the eyes. We've seen immune system changes where some responses weaken and others become overactive. The gut microbiome shifts in microgravity and enclosed habitats, and that can influence digestion, immunity, even mood. But we don't have solid data on what happens when you stack all of this — microgravity, radiation, isolation, altered sleep cycles for multiple years, and then add partial gravity in the middle. You're pushing human physiology into a regime where we have more questions than answers. So the obvious thought is, can we cheat gravity? If microgravity is wrecking the body, can we bring gravity with us? At least a fake version of it. One proposed fix is centrifugal artificial gravity. Spin the part of the spacecraft so that the outward push you feel standing on the inside of the ring mimics gravity. If you spin at the right rate and make the radius large enough, you can simulate anything from Mars's 0.38 G up to Earth's 1 G. But the engineering is not simple. If you spin too fast, people get dizzy, disoriented, and sick because the inner ear doesn't like high rotation rates. So you keep spin rates low, maybe around 2 revolutions per minute or less. To get useful gravity at that spin rate, the radius of your rotating structure has to be tens of meters. That's no longer a compact capsule. It's a giant rotating building in space with bearings, joints, and structural elements that all have to survive launch, assembly, and years of operation. You're far beyond Apollo capsules or ISS-style modules. You're designing and constructing something we have never actually flown before, and then betting your crew's health on it. Even if you pull off artificial gravity during the cruise, there's a second shock waiting at the end of the mission, coming home. After living at 0.38 G on Mars, your body will adapt to that environment. Muscles, bones, cardiovascular system all will reset to what is needed there. Then at the end of the mission, you land back on Earth at 1 G again. Suddenly you're heavier. Every movement takes more effort. Your heart has to push harder. Your bones and joints are under more stress. Recovery might take months. Walking can be hard, running is out of the question for a while. If there's an emergency on landing, say a rough touchdown or a capsule that flips, or a fire, you have to assume the crew is physically fragile. Rescue teams and procedures must be built around the idea that this is not a group of fully capable athletes stepping off a plane. It's a team whose bodies have been through years of unusual stress and multiple gravity shifts. So even if the rockets work, the landers work, the habitats work, and the ISRU plants run perfectly, the limiting factor may still be the human body. The hardware can be overbuilt, but your bones and neurons and immune cells can't be swapped out in a maintenance bay. And that leads to a different kind of threat, one you can't patch with a wrench or shield with a regolith. What all of this does to the mind. Because it's not just your skeleton and heart doing this mission, it's the part of you that has to live in a tin can with a tiny crew years from home, with delayed messages and no quick escape. So the next question is brutal and simple. What happens to your psychology, your group dynamics, and your sense of reality when Mars turns your life into a long, high-stress isolation experiment with no way to tap out? You can handle danger when you know there's a way out. So what happens to your head when you know there isn't? That's the first psychological punch Mars throws at you, and it's not subtle. On the Moon, you always know Earth is a few days away, roughly 3 days to fly back, a few more to be on the ground. That knowledge sits in the back of your mind as a safety net. It's risky, but it's not sealed off risky. On Mars, you're between about 56 and 400 million kilometers away from home, 35 to 250 million miles. You're not far. You're so far that rescue is physically impossible during your mission. If something fails badly, no one is coming. Not this week, not this month, not at all. That distance becomes a psychological horizon. You don't just know the numbers, you feel what they mean. Every alarm, every odd reading, every strange noise in the habitat carries the weight of we fix this ourselves or we don't survive. That constant awareness can sharpen you, but it also grinds you down over months and years. Stress is no longer a spike, it's a baseline. Then add who you're stuck with. A Mars crew is not a large group. Mass and life support will probably cap it at around 4 to 6 people. That's smaller than many Antarctic winter crews, and way smaller than a town or even a big office. Every person is critical. Everyone has multiple roles. Engineer, medic, scientist, mechanic, maybe psychologist, all in one. There is no rotation of fresh staff, no new faces showing up to reset group dynamics. Your social world is fixed for the entire mission, maybe 900 days or more. If someone's habits annoy you, they will annoy you for years. Or if conflict starts, there's no real escape. You work with the same few people, eat with them, exercise with them, see them in every shared space. Privacy is limited. That turns small frictions into serious risks if you don't manage them. Now layer in time itself being slightly wrong. On Mars, the day, the soul is about 24 hours and 39 minutes. It sounds like a small difference, just 39 minutes longer than an Earth day, but your body's clock is tuned to roughly 24 hours, not 24 and a bit. NASA teams that operate rovers already know this. When they sync their work schedule to Martian time, their sleep shifts later and later relative to local time on Earth, and it starts to strain their health and mood. For a crew on Mars, if you don't manage this carefully, you can drift into chronic circadian disruption. Your sleep gets fragmented, you feel jet-lagged all the time, your reaction times drop, your emotional control weakens. Over weeks and months, that can feed anxiety, depression, irritability, and bad decision-making. You need lighting schedules, strict sleep protocols, and maybe even pharmacological help just to keep your internal clocks aligned enough to function. Then there's the way Mars breaks your connection to Earth's rhythm. You don't get live sports, live events, or live anything. Because of the communication delay, everything is time-shifted. News arrives late, reactions to your own updates come long after you send them. You never share a real-time moment with anyone back home. That delay plus limited bandwidth means your information environment is curated and buffered. You get what fits in the pipe and what mission planners prioritize. Over time, Earth's daily chaos becomes a distant background, not your reality. You are literally in another place and, in a sense, in another time. The world moves on and you watch it in delayed, compressed clips. That can intensify the feeling that you're no longer part of Earth's story, just an observer. All of this means you can't treat psychology as an add-on. You can't say, we'll send tough people and they'll handle it. You have to design the social system of the mission as deliberately as you design the life support. That means protocols for conflict resolution that are taken seriously, not just written in a manual. How do you handle two crew members who can't agree? Who mediates? How do you de-escalate arguments in a habitat where no one can leave for a walk outside without a suit and a plan? You need clear roles, but also flexibility, so people don't get trapped in identity conflicts like, I'm always the one blamed for X. You also need structured psychological support. That can mean regular private sessions with Earth-based professionals over delayed video, mental health checklists, anonymous reporting tools for stress and conflict, and training in basic counselling skills for crew members. Everyone needs to know the signs of burnout, depression, and breakdown, both in themselves and in others. Private time is not a luxury, it's a survival tool. Habitats must include real personal space, even if it's small. A private berth, a door that actually closes, sound isolation where possible. People need time where they are not on, not observed, not responsible for anyone but themselves. Without that, irritation and fatigue stack up dangerously fast. Rituals and celebrations sound soft, but they matter. You're pulling people out of every normal cultural pattern they know. No weekends in the usual sense, no local holidays, no spontaneous nights out. You need to build a mission culture on purpose, shared meals, fixed off-duty times, celebrations for milestones, birthdays, holidays adapted to Mars time. Those routines give structure to a long, featureless stretch of days and help anchor mental health. You're also dealing with hierarchy and authority in a very intense way. There will be a chain of command, but you can't run a Mars base for 900 days without cracking people. At the same time, you can't have loose, vague leadership in emergencies. You need a balance, clear authority for safety and operations, but with real input, transparency, and psychological safety so people can raise concerns without fear. Designing that balance is not trivial. It's sociology and leadership science under extreme conditions. So a Mars mission forces space agencies and companies to think in disciplines they aren't used to leading with: sociology, anthropology, organizational psychology. It's not just, can the hardware run for 900 days? It's, can this tiny society keep functioning without tearing itself apart, in a place where a fight, a breakdown, or a bad decision can have lethal consequences? And even if you get the human side mostly right, if your crew is stable, trained, and supported, you still run into one more layer that makes Mars so much harder than the Moon: the mismatch between what engineering risk demands and what public opinion will actually tolerate. Because it's one thing to accept danger on paper, and another to launch a mission where you know, realistically, that some crews may never come back alive. So the next question is sharp and uncomfortable. When the physics say high risk is built in, but modern society says failure is unacceptable, how do you even decide when to go, and how much risk you are willing to load onto the first people who try? You can make the hardware safer and smarter every year, so why does a Mars mission still feel like something leaders are scared to sign off on? The gap isn't just in engineering, it's between what the physics demands and what public opinion will actually accept. In the Apollo era, the risk envelope was huge. People in charge knew that Apollo 11 had a real chance of failing in a way that killed the crew. There were contingency speeches written for the scenario where the astronauts were stranded on the Moon with no way back. That wasn't a dramatization, it was taken seriously. The engineering was as precise as the tools of the time allowed, but society was willing to accept a high chance that something might go fatally wrong. Because the Cold War stakes were massive and the race to the Moon was treated like a national emergency project. That attitude let NASA move fast. They stacked missions close together, accepted design margins that would make today's reviewers uncomfortable, and pushed new systems into service after comparatively short test campaigns. That doesn't mean they were careless, but it does mean the accepted probability of losing a crew was far higher than what most people would tolerate now. Today the tolerance is much lower, and that change is not theoretical. Accidents like Challenger in 1986 and Columbia in 2003 killed astronauts on the live television. Investigations expose flaws not only in hardware but in culture and communication and decision-making. The lesson burned into the system was clear. One high-profile failure can freeze the program, trigger backlash, and reset public trust to zero. Now apply that mindset to Mars. By its nature, a Mars mission has stacked risks: long duration, no easy abort, radiation, complex EDL, heavy dependence on new technologies like large-scale ISRU and long-life closed-loop life support. Even with conservative design, realistic early mission estimates may show a mission mortality risk of a few percent, possibly higher at first. That number may be acceptable to some astronauts who volunteer knowing the danger. You're asking governments, agencies, or companies to sign off on a mission where serious harm is not just possible but statistically expected over multiple flights. Then look at abort options, because these directly feed into how risk feels, not just what the numbers say. On the path to the Moon, Apollo had several abort modes. During launch, you had escape systems. In translunar flight, you could sometimes adjust trajectory and come back early. Free return trajectories existed where, if the engines failed after a certain point, you would still loop around the Moon and head home. In the worst case, as Apollo 13 showed, you could use the lunar module as a lifeboat and still return in a few days. None of that exists in the same way for Mars. Once you perform the big burn that sends you on a Trans-Mars injection, you're effectively on rails. The only meaningful abort is to skip landing and come back when orbital geometry allows a return burn, and even that takes many months. That is not emotionally similar to an airplane turning around mid-flight or a lunar mission doing a quick loop home. When something goes badly wrong on a Mars mission, everyone knows there is no rescue mission coming, no fast reversal, only mitigation and damage control in place. So how do engineers respond to that? By trying to drive down risk with redundancy, testing, and over-design. If one pump can fail, you add a second. If one computer can glitch, you add a backup and a backup to the backup. You test subsystems in multiple environments. You run long-duration endurance tests. You design structures with extra safety factors. You add sensors, diagnostics, and fail-safe modes to everything. All of that works to reduce risk, but every layer has a cost. More redundancy means more mass and more complexity. More complexity means more interactions between systems, which can create new failure modes. More testing means more time and higher program costs. The Moon got away with less of this because the total exposure per mission was short. Mars doesn't give you that option. Public perception multiplies everything. If a Mars mission goes wrong early, especially if it fails dramatically with loss of life and clear visuals, it doesn't just hurt that mission, it hits the entire concept of human deep space flight. Billions or tens of billions of dollars invested, years of hype, and then a catastrophe broadcast across the planet. That is exactly the kind of event that can cause major governments to say no more for a generation. Agencies and companies know this, so they move slowly. They insert extra test flights, uncrewed demos, long-duration ground runs. They demand higher technology maturity levels before flying hardware on crewed missions. Each of those steps adds years. A Mars architecture that might be technically feasible in a decade can easily stretch to 2 or 3 decades under the weight of cautious validation. So you get a paradox. The safest way to go to Mars is to take your time, test everything, and add redundancy. But the longer you stretch the timeline, the more you expose the program to budget cuts, shifting priorities, and loss of momentum. Meanwhile, technologies evolve, designs get updated, old test results become less relevant, and you end up constantly chasing a moving target. And even if you somehow thread that needle, balancing an engineering margin, getting enough risk reduction without stalling for half a century, there's still the final bottleneck: money and commitment over the long haul. Because every mitigation, every new test, every extra backup system has a price tag, and Mars is not just a project you fund for a few years, it's something you have to feed with resources over multiple decades of shifting governments and competing priorities. So the next hard question is this: if Apollo needed a Cold War rivalry and huge slices of national budgets just to reach the Moon for a few short visits, what does it actually take financially to build and sustain the kind of multi-decade Mars campaign we've been talking about? And why hasn't that happened yet, despite all the talk? You can have the rockets, the habitats, the ISRU plans, the medical protocols, and still never leave Earth if one thing doesn't line up. Money, held steady for decades. That's the part people like to skip in the glossy animations, but it's exactly where Apollo and Mars diverge. Apollo was not just a science project. In the 1960s, the United States spent around $25.4 billion on Apollo, which in today's money is usually quoted as more than $250 billion. At its peak, that was on the order of 4% of the entire US federal budget. That's enormous. Imagine 4 out of every $100 of government spending flowing into one program. Why was that even possible? Because Apollo was framed as a Cold War move, a signal to the Soviet Union and to the rest of the world that the US could do something no one else could. It was sold as national security, national prestige, and ideological competition. That gave a reason to accept huge costs and serious risks over a short, intense burst of time. The mission was clear: beat the rival to the moon. Now look at Mars. There is no current superpower race to land humans there. No head of state is on TV saying, we must reach Mars before they do or we lose. Without that direct rival, you lose a massive piece of the justification for Apollo-level spending. Instead, funding for Mars-related work is more like a series of nudges. A bit more money one year, a bit less the next. New studies, revised roadmaps. Stop-start, stretched and vulnerable. Every time a budget tightens or priorities shift, Mars slips down the list. You don't get the same concentrated fire hose of resources Apollo had. You get a long, irregular drip. Then there's the brutal mismatch between how long a Mars program actually takes and how short attention spans really are. A serious Mars architecture might need 20 or more years from "we are funding this seriously" to first humans land. That's designing the rockets, testing them, building deep space habitats, perfecting EDL for heavy payloads, proving ISRU, doing uncrewed dress rehearsals, and then finally flying crews. In many democracies, election cycles are 4 or 5 years. Over 20 years, you're talking about 5 or more different governments or administrations. Each one can tweak, delay, or cancel parts of the program. A leader leaves, a crisis hits, budgets are cut, and long-term projects look like easy targets. The Moon benefited from a compressed timeline. From Kennedy's speech to Apollo 11 was about 8 years. Mars suffers because you can't compress it that way without taking insane risks. So if governments alone are too slow and cautious to eat this whole cost the Apollo way, who else steps in? This is where commercial players start to matter. Companies pushing fully reusable rockets and in-orbit refueling aim to take the cost to low Earth orbit from something like $10,000 per kilogram down toward $100 per kilogram, maybe even lower if everything works perfectly. If that actually happens, the economics change dramatically. Getting hundreds or thousands of tons of hardware into orbit no longer looks like burning national treasure. It starts to look like a very expensive, but not insane industrial project. Cheaper mass to orbit means your Mars ships, habitats, fuel tanks, and ISRU machines stop being fantasy-level expensive. You can afford to build, test, and iterate more. You can throw away early versions if they fail, instead of treating every piece of hardware as sacred because it costs too much to replace. But there's a catch. Those commercial systems have to prove themselves at scale. Not once, not twice, but over and over with high reliability. Until that happens, all the promised cost curves are just that, promises. Even if launch gets cheap, Mars still looks like something no single country or company wants to own completely. That points to an international approach. Multiple space agencies, multiple firms, shared infrastructure, shared risk, and shared credit. That sounds good on paper, but coordinating that over multiple decades is a different kind of nightmare. You need agreements on standards, docking ports, communication protocols, fuel types, safety rules. You need treaties on who is responsible for what, who gets to decide landing sites, how you handle accidents, how you share data. You need to coordinate contributions. This country builds a habitat, that one builds a power system, this company delivers cargo, that one handles crew transport. And you have to do it while governments change, economies rise and fall, alliances shift, and public interest waxes and wanes. Physics is stable, human institutions are not. A reactor doesn't care who's in office, a budget line does. Over 20 or 30 years, that volatility can be as deadly to a Mars program as any radiation burst. So when you step back, you see the full picture. The technology can slowly line up, the engineering can chip away at risk, but you still need a level of financial commitment that holds steady across multiple election cycles, multiple crises, and multiple leadership changes. Apollo had a rival, a compressed timeline, and a clear narrative. Mars has a diffuse set of benefits, a very long timeline, and no single easy story that fits into a campaign speech. And that leads straight into the next hard question. While all this money stuff drags on, what is actually ready right now and what is still vaporware? Because it's one thing to talk about reusable rockets, ISRU, artificial gravity, and closed-loop life support. It's another thing to ask today, which of those have we truly proven and which are still just slick animations in a presentation? You keep hearing people say, we already have the tech to go to Mars, so why are we still in low Earth orbit and on PowerPoint slides? The answer is, a lot of what we talk about is real, but it's proven in narrow ways, under friendly conditions, and not yet at the scale or combination a Mars mission needs. Look at what we actually nailed with the Moon. There, we demonstrated precision trajectories, aiming spacecraft so they hit a tiny moving target around Earth. We proved we can do powered landings in vacuum, riding rockets all the way down to the surface with fine control. We docked vehicles in lunar orbit, joining separate spacecraft in a place where a mistake means losing both. We did spacewalks, EVAs in hard vacuum, working outside the ship in suits that kept people alive. We even did sample return rock and soil from the Moon back to labs on Earth. That's an impressive list. It proves we can navigate, land, dock, walk in suits and come home with cargo. But all of that happened under short mission timelines, days to maybe 2 weeks, and near-Earth conditions. Radio delay was small, resupply was impossible, but return was fast. Radiation exposure was limited, and life support didn't have to last for years. The Moon gave us a strong base, but it did not test the long-haul systems Mars needs. Now look at Mars itself and what we've already done there with robots. We've orbited Mars many times with different spacecraft, mapping the surface, studying the atmosphere, watching seasons change. We've landed probes and rovers on the surface with increasingly complex entry, descent, and landing systems. Those rovers have driven tens of kilometers over years dealing with dust, temperature swings, and mechanical wear. We even flew a helicopter, Ingenuity, in Mars's thin air. That showed we can generate lift and control flight in an atmosphere that's less than 1% of Earth's surface pressure. On top of that, we've run ISRU experiments like MOXIE, which took Mars's CO2 and turned it into oxygen on the spot. That's a direct proof that the chemistry needed for future oxygen and fuel plants isn't just theory, it works in real Martian air. Those are crucial pathfinders. They tell you that landing robots, driving around, flying small craft, and doing basic in situ processing are possible. But the question you have to ask next is simple. What have we not done yet that a human Mars mission absolutely depends on? Here's the short list of big gaps. We have never landed payloads of tens of tons on Mars. Our largest landers and rovers are around 1 ton. That's tiny compared to the 28 to 40 ton class you expect for a human lander or a major habitat. We have not run a full closed-loop life support system for an entire Mars mission duration, something like 2.5 years, without steady resupply. The ISS gets cargo ships all the time. A Mars ship doesn't. We have not demonstrated large-scale ISRU fuel plants that take CO2 and water and produce tons of methane and oxygen in a real planetary environment for years without constant human maintenance from a full team. And we have never operated rotating artificial gravity structures in space with radii of tens of meters at stable spin rates, with humans living inside them long term. Every single one of those missing pieces is a linchpin for safe, repeatable Mars missions. Without them, you're leaning on unproven systems in the most unforgiving scenario you can pick. Even the parts that seem mature, like reusable rockets, are not at full Mars campaign level yet. Reusable boosters landing themselves are a genuine revolution. They do powered descents from speeds of around 2 to 3 kilometers per second, about 4,500 to 6,700 miles per hour, and touch down on landing pads or drone ships. That proves we can save hardware, cut costs, and test advanced guidance and propulsion in real conditions. But turning that into something that looks like an airline-like service is another step. For Mars, you don't need 1 or 2 launches a year. You may need dozens, maybe hundreds, to loft habitat modules, tankers, ISRU gear, rovers, power systems, and eventually crews. You need these vehicles to fly often, reliably, with short turnaround and high confidence. You need a logistics chain where launching 100 tons to orbit is just another Tuesday, not a historic event. We're moving in that direction, but we're not there yet. The hardest part isn't any single technology, it's the pile of them you have to run at the same time. A crewed Mars mission is not one system, it's a tech stack that looks more like a web than a ladder. You need high-energy launch vehicles to get big masses into orbit. You need either in-orbit assembly or in-orbit refueling, probably both, to build and fuel the deep space ship. You need interplanetary habitats that can keep people alive and functional for many months. You need the EDL systems we talked about, capable of landing heavy cargo and crew safely through Mars's awkward atmosphere. On the surface, you need habitats that tolerate dust, cold, and radiation for years. You need ISRU plants that take in CO2 and ice and spit out fuel, oxygen, and water, running mostly on their own. You need Earth return vehicles that can sit for months on Mars, fueled and reliable, then light up and bring people home. Each one of these has to work, and they all have to interlock, timing-wise, interface-wise, and failure mode-wise. Apollo, for all its complexity, was basically a vertical stack. Big rocket, command module, service module, lunar module, and a short mission chain. Mars is a web of interdependent systems. A delay in one area can stall the rest. A design change in one element can ripple through docking standards, mass budgets, and power demands everywhere else. You're not just building a spacecraft, you're building a small distributed infrastructure in space and on another planet. So when people say, "We have the tech, we just need the will," the honest answer is, we have pieces of the tech and they are getting stronger every year. But the fully integrated end-to-end system that takes humans to Mars keeps them alive for years and brings them back repeatedly and safely. That system is still under construction, in labs, on test stands, and in early prototype missions. And even that isn't the final trap. Because the Moon already taught us one more thing that Mars throws right back in our face. Doing something once under special conditions is not the same as making it routine under worse ones. The Moon, in hindsight, was the training ground, the tutorial level that showed us how to play the game without actually telling us how hard the later levels would be. So the next question is this: if the Moon gave us so many wins, why does that experience still fall short when you scale up to Mars? And how does using the Moon as a testbed now actually change our odds of surviving the first real push to the red planet? You'd think that once you've orbited another world and landed people on it, the rest of the solar system is just more of the same. The Moon should mean we've passed the test, right? The twist is, the Moon was less a final exam and more a tutorial level that let you make mistakes close to home. Look at how fast the Moon let you learn. From Apollo 8, the first crewed lunar orbit, to Apollo 11, the first landing, took about 7 months. That's nothing in space program time. Missions flew multiple times per year. Apollo 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, all within a few years. Each flight brought back data. What broke, what nearly broke, what worked better than expected. Engineers patched software, refined procedures, adjusted hardware, and saw the results on the very next mission, sometimes the very next year. Short feedback loops like that are gold. If your guidance system has a quirk, you see it, fix it, and verify the fix quickly. If the suits chafe in a certain joint, you can redesign and test again in a short time. Risk drops fast when every experiment gets a near-term follow-up. The moon's short travel time and frequent windows made that possible. Now ask yourself, what happens when your next experiment is one launch window away 26 months later and the mission lasts 900 days instead of 10? The logistics chain was also much cleaner for Apollo. Everything came directly from Earth. You launch one huge rocket from one planet and you send the entire mission stack, command module, service module, lunar module, supplies, all of it. No orbital depots, no propellant transfer between vehicles, no pre-deployed fuel factories sitting on the surface, no coordination between multiple launch campaigns just to assemble one ship. That's the camping trip model. You load up your car, in this case the Saturn V, with everything in the trunk. You drive to the campsite, stay a few nights, then drive home. There's no shipping containers that have to leave 3 months earlier, no separate cargo ship with your food and tools. For Mars, the second you try that same approach, the mass and cost blow up. You're forced into a shipping and staging model. Cargo first, fuel plants first, habitats first, humans last. That's a supply chain, not a single mission, and it comes with all the failure points of a complex logistics network. The moon also limited the number of domains you had to master at once. Apollo had to deal with vacuum operations, short-term microgravity in transit, and basic life support for days, not years. Radiation exposure was limited, surface gravity was low but constant, and the environment was harsh but simple. No atmosphere, no weather, just extreme temperature swings and abrasive dust. Mars is a stack of domains on top of each other. You have vacuum in space, thin atmosphere aerodynamics for entry and descent, multi-year life support without resupply, surface operations in a new gravity field at 0.38 G, and a radiation environment worse than low Earth orbit. You can't treat these as separate problems. Your EDL profile affects where you can land ISRU hardware. Your power systems affect what life support can run. Your radiation shielding mass affects your rocket design. Every piece couples to the others. The moon let you isolate a few problems. Mars forces you to solve many at once. That's why current plans drag the moon back into the spotlight as a proving ground instead of just a trophy. If you're smart, you use the moon to practice what you'll need on Mars, but with a safety net only 384,400 kilometers away, instead of tens or hundreds of millions. You test surface habitats in real vacuum and real dust, see how seals and materials hold up after hundreds of days, not just 75 hours. You try ISRU on lunar ice in permanently shadowed craters, learning how to mine, melt, purify and store water pulled from another world. You run long-duration missions in partial gravity, maybe on a lunar base, to see what months in 0.17 G do to the body. You practice operating with delayed but not Mars-level communication lags. When something fails, you can still send a rescue mission, or bring people home in days, not years. The moon becomes your lab for risk that would be unacceptable if the first trial run were on Mars itself. But here's the emotional trap. Because humanity already did the moon, it's easy to mentally downgrade it. People say, we've planted flags there, we've driven rovers, we've brought back rocks, so going to Mars is just further. That mindset is dangerous. Distance here is not just a bigger number on a map. It's a multiplier on every risk and every uncertainty you've been stacking up through this whole story. Every step beyond the moon pushes you into a regime where no human has ever lived. No one has lived in deep space for months without Earth's magnetic protection. No one has operated a base for years in an environment like Mars's thin, toxic atmosphere and global dust storms. No one has run full closed-loop life support at scale, in real interplanetary conditions, for the entire span of a Mars mission. Your margin for error shrinks, while the time it takes to observe, fix, and iterate stretches out. So the moon isn't a sign that we've mastered human spaceflight. It's proof that we can pass the early levels. Mars is the next level, where the game rules change mid-play. Distances explodes, abort options vanish, system complexity spikes, and psychological limits get hit long before the physics do. And that brings you to the final hard question in this chain. If the moon was the tutorial and Mars is the first true boss fight for a spacefaring civilization, then when do you actually step up? What conditions need to be met before it's not reckless to send people? And what does that first wave of real Mars missions actually look like compared to the clean, heroic stories we like to tell? So when do you stop talking about Mars and actually put people on a rocket, knowing everything you've just heard? The honest answer is, you don't get a magic date, you get a checklist. You only go when enough of that checklist is real hardware, not slides. First question you have to face is simple. What do you absolutely need to see working before you risk a full crew? You're stacking precondition, not wishes. You need heavy lift rockets that are not just flying once in a while, but launching routinely, landing and flying again. You need in-orbit refueling that is proven, which means pumping hundreds of tons of cryogenic propellants between tanks in microgravity without leaks, slosh disasters, or surprise boil-off. You need long-duration life support demos, not for 6 months, but for mission-level lengths over 2 years, with no resupply except what you simulate. You need large-mass EDL tests at Mars itself, not another 1-ton rover, but serious multi-ton cargo landers that prove you can get big pieces of infrastructure down safely. And you need working ISRU prototypes that don't just run in a lab, but sit on a real world, take in real CO2 and real ice, and produce real oxygen and methane for months or years. Each one of those is a multi-year project on its own. None of them are nice to have. They're preconditions for a mission that isn't just a stunt. Once you admit that, the next question is, what does that first human push actually look like? Is it a single giant mission, or something slower and more controlled? A realistic answer is, it's a campaign, not one heroic shot. Mars is not going to be one big flag-planting moment and then credits roll. The sequence is more like, first robotic ISRU, plants go in. They land, unfold solar arrays or hook to reactors, start pulling in air and ice, and quietly build up stocks of oxygen and fuel. Then cargo bases arrive, habitats, power systems, spare parts, big rovers, more reactors, more tanks. Those landers touch down, link into the existing infrastructure and expand it. Only after that do you send short human sorties, missions where crews land, stay for weeks to a few months, and then leave while the systems are still heavily backed up by Earth. If those work, you stretch the stay times, 6 months on the surface, then a full synod over 500 days. Eventually you stop talking about missions and you start talking about outposts that never fully shut down. That's a timeline measured in decades, not in a single 5-year plan. If that frustrates you, that's good. It means you're paying attention to how hard this actually is. Then there's the propulsion question. Do you stick with chemical rockets forever? Or do you change the engine under the whole concept? Chemical propulsion works, but it's slow and fuel-hungry. New ideas like nuclear thermal rockets, TRs, try to bend that curve. An NTR heats hydrogen propellant with a nuclear reactor instead of burning it with oxygen. That gives you higher specific impulse, which basically means you get more push per kilogram of propellant. Numbers vary by design, but you can push your transit time down to around 3 to 4 months instead of 6 to 9. That cuts radiation dose, shrinks how much food and water you need to carry, and reduces the time your hardware has to survive in deep space. But now you've traded one set of problems for another. You're flying a nuclear reactor in space, possibly doing burns near Earth orbit and Mars orbit. You have to prove that the reactor is safe in launch accidents, safe in operation, and safe when the mission ends. You have to deal with international treaties, public fear of nukes in space. NTRs might be worth it, but they add a layer of nuclear safety on top of everything else you already have to solve. Even if you build the perfect engines and the perfect campaign plan, you still have to be brutally clear about what life looks like for the people on that first wave. If you picture them as explorers casually walking around taking selfies with mountains in the background, you're missing the point. The first humans on Mars will be test pilots and mechanics more than anything else. Their job is not to enjoy the view, it's to make the systems work without failing. Most of their time will go into checking valves, fixing leaks, diagnosing weird readings in fuel plants, cleaning dust out of suit joints, recalibrating sensors, patching cracks, and updating software. They'll be operating drills to reach ice, repairing compressors that seize in the cold, swapping filters in CO2 scrubbers, and performing maintenance on nuclear or solar power units. Their day will be built around checklists, not exploration freedom. Wake up, health checks, system checks, repairs, reports, more system checks, maybe a short traverse outside for targeted science or maintenance, then back inside for more diagnostics and planning. The big goal of those first missions is to prove that humans and machines together can run a base without catastrophic failure, not to conquer anything in a romantic sense. They're more like extreme environment plumbers, electricians and field engineers who happen to have a whole planet outside the window. So with all of this stacked against you, distance, radiation, life support, psychology, cost and more, why does Mars still sit at the centre of long-term human spaceflight plans instead of being quietly abandoned? The answer is not hype, it's that Mars checks more of the boxes for a second home than anything else we can reach in our lifetime. Mars has day and night cycles close to Earth's, about 24 hours, 39 minutes per sol. That makes human schedules and power planning much easier than places with wildly different rotation periods. It has seasons driven by its tilt, which means a climate system you can study and eventually forecast and adapt to. It has accessible water ice not just locked away at the core, but in polar caps and buried deposits which can feed drinking supplies, agriculture and fuel production. It has solid ground, rock and regolith you can build on, dig into, and use as shielding and construction material. No other place we can realistically send humans to in the next century combines all of that. The moon is close, but it has no thick atmosphere and far less accessible water away from the poles. The big icy moons are too far and too deep in giant planet radiation belts. Free-flying habitats in space might be built one day, but they don't give you a whole world's worth of raw material and gravity ready-made. The moon proved one thing: we can leave Earth, survive in space for days, and come back with our story intact. Mars asks a harder question. Can we go somewhere else and actually stay, building a system where local resources, human skill and robust engineering combine into something that doesn't fall apart the moment a cargo ship from Earth is delayed? If the answer to that question is yes, even once you've crossed a line in human history that never uncrosses. For the first time, life from Earth would be living off Earth in a way that has a chance to outlast short-term luck. That is why, despite every difficulty you've heard, Mars remains the place where the future either expands or stays locked to one fragile planet. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.